Hello friends, welcome back to my YouTube channel. This is part number 9 of my discussion on liquid extraction, and in part 8 I had started discussing stage-wise liquid extraction. In the previous video I discussed single stage liquid extraction, and today I will be solving a numerical, or I will be discussing a numerical that is based on the single stage liquid extraction operation. So let us start the discussion. First, let us look at the numerical statement. So 100 kg of a solution of acetic acid and water containing 30% acid is to be extracted in a single stage operation with isopropyl ether as the extracting solvent. The operation is carried out using 40 kg of solvent at 20 degrees Celsius. Find the quantities of raffinate and extract phases produced in this operation. So you have a solution of acetic acid and water. We have 100 kg of the solution, 100 kg of the solution of acetic acid and water, and the solution is containing 30% of acid in it, and this is to be extracted in a single stage extraction operation. The solvent used is isopropyl ether, and the operation is carried out by using 40 kg of solvent, and it is carried out at a temperature of 20 degrees Celsius. And we are supposed to find out the quantities of raffinate and extract phases. And we have been provided with the equilibrium data. The equilibrium data is given in this table. You have water layer, which is in equilibrium with isopropyl ether layer, and in each layer percentage weight of the three components. In this case, A, in our discussion, A is the carrier solvent, which in this case is water. Then B is the extracting solvent, in this case it is isopropyl ether. And the solute to be extracted, we denote that by C, and in this case it is acetic acid. So we have a ternary system of water, isopropyl ether and acetic acid, and the data when the two layers, water rich layer and isopropyl ether rich layer, they are in equilibrium with each other, composition of each layer is given to us. We have different equilibrium compositions. The compositions are given in percentage weight. So you have percentage weight of A, percentage weight of B, percentage weight of C. And in isopropyl ether layer also we have percentage weight of A, percentage weight of B, and percentage weight of C. Okay, so first let us list the given data. You have the feed solution. It is solution of acetic acid and water. So acetic acid we are denoting by C, and water we are denoting by A. So you have A plus C solution, the feed solution. The quantity of feed is given to us, it is 100 kg. It is a batch operation and the quantity of feed is 100 kg. Then weight fraction of C, that is weight fraction of acetic acid in the feed, is given to us. It is 0.3. Then the solvent to be used in the operation is pure isopropyl ether. That means in the solvent phase you have just isopropyl ether. There is no presence of acetic acid and A in it. If it was a reused recovered solvent, then the solvent phase would be containing all the three components. But over here, since pure solvent is being used, it will contain only solvent in it. That means Ys, which is weight fraction of C in the solvent, it is 0, and Nys, which is weight fraction of B in the solvent phase. The solvent is pure B, that's why the weight fraction of B in it is 1. And the quantity of solvent that is being used, that is also given to us, it is 40 kg. So that means it is S1 is 40 kg. Solvent going to stage number 1. I am denoting that as S1. So S1 is 40 kg. Then the equilibrium data is given to us. So you have composition in weight percentages of raffinate and extract phases. They are given to us when they are in equilibrium with each other. Raffinate in this case is the water layer, and extract phase, it is the isopropyl ether layer. And what are we supposed to find? We are supposed to find the quantities of raffinate and extract phases that are produced. That is, we need to find out R1 and E1 in kg. Amount of raffinate in kg and amount of extract in kg. Okay, so with this given data, let us solve the numerical. Let us go for the solution. First of all, we will represent the operation with the help of a schematic diagram. So this circle, let this circle represent the stage. So feed is going to the stage. Feed is 100 kg. It is contacted with solvent. Solvent that is used is 40 kg. So it is going to stage number 1, and then there will be mixing of the two phases. So there will be mixer in the stage, and then after mixing is done properly, it is allowed to settle. So we need a settler. So after settling, the two layers, that is raffinate layer and extract layer, they are removed. So we are supposed to find out quantities, this R1 and E1. Okay. So first of all, the first step is we will be doing calculations for the mixture. What is this mixture? We are talking about that mixture which will be formed after mixing feed and the solvent. So let us do the calculations. So mixture will be formed after feed and solvent are mixed. So that is M1, mixture in kgs, is equal to feed in kg plus solvent in kg. So therefore M1 is equal to feed is 100 plus 40, that is M1 is equal to 140 kg. Then we will find out weight fraction of C in the mixture. We denote that by XM1. So XM1, the equation for finding XM1 is this. I have derived it in my previous video when I discussed material balance for single stage extraction. So I am directly taking that equation. XM1, that is weight fraction of C in the mixture, is equal to FXF plus S1YS divided by M. Now all quantities are known to us. All quantities on the right hand side, they are known to us. Let us use those quantities to get the value of XM. So XM, what quantities? XF is known to us, it is 0.3. YS is 0 because you are using pure solvent. And then S1 is 40, So you just put the values. That will give us XM1. So XM1 is equal to 100 because F is 100. 100 into 0.3, XF is 0.3 plus 140. S1 is 40. S1 is 40. So XM1 is equal to 100 into 0.3 plus 40 divided by 140. That gives us XN1 as 0.21. So at this point of time, we have got the weight fraction of C in the mixture. We denote that by XM1. And now we are going to use this in our calculation. Okay, let us continue. Now, the next task is we will plot the graph. And for plotting the graph, because we will be showing this material balances on the equilibrium diagram. So for plotting the graph, we are going to use the data, equilibrium data that is given to us. And from the given data, we will find two more quantities for each layer. NX, this is weight fraction of B in water layer. X, weight fraction of C in water layer. And how are you going to get it? Weight percentage of B is given to us. So you simply divide the percentage value with 100. You are going to get weight fraction of B. Similarly, weight percentage of C is given to us. Again, we'll have to divide that with 100 to get weight fraction. So accordingly, you get those values. 1 by 2 by 100 is 0.012. Then 1.5 divided by 100 is 0.015. 1.6 divided by 100 is 0.016. So accordingly, all other values I am taking in this table. Now let us get the fraction of C in water layer. How are we going to get that? We are going to get by dividing the percentage value with 100. So 0.69 divided by 100, 0.0069. 1.49 divided by 100 is 0.0141. And accordingly, all other values I have written in this table. So simply percentage of B is converted to weight fraction of B and percentage of C is converted to weight fraction of C. Similar calculations are done for the isopropyl ether layer. So accordingly, you get weight fractions of B, which are obtained by dividing weight percentage of B with 100. So you get all the values. Similarly, weight percentage of C is converted to weight fraction by dividing the percentage value with 100. And if you do it for all the given values, this will be the Y values. Okay, so we have calculated fractions of B and C in each layer, and we are going to use these values for plotting the graph. Okay, so let us plot the graph. So on the x-axis, we will be plotting nx and ny, and on y-axis, we will be plotting x and y. So plot will be, we will be plotting nx versus x and ny versus y. So the given data is now plotted and you get this curve. So I'm showing simultaneous points for the two layers. So this is water layer, this is isopropyl ether layer. And since these are equilibrium concentrations, they will be connected by a tie line. The next pair of points is, this is the point in water layer, this is the point in the isopropyl ether layer, and now they are connected with a tie line. So in this way, all points are plotted and corresponding points, they are connected by the tie line, by a tie line. Why? Because those are concentrations that are in equilibrium with each other. So this gives us the binoidal solubility curve, and now we are going to follow the material balances on this graph. Now first task is to locate F. So we know in my previous discussion I have discussed how to locate F. So for locating F we need this point, a point whose coordinates are point F will be having coordinates of 0 and xf, and xf is 0.3, so the point will be having a coordinate of 0 and 0.3. So that point is located at over here. Xf is 0.3 and that will be point F. Then we have to locate point S. Point S will be located with, point S will have coordinates of NYS 0. NYS is 1 because pure solvent is used. So point S has coordinates of 1, 0. So it will be located over here. So this is point S. So after locating point F and S, next task is we have to connect F, S with a straight line. So we are going to do that. So F and S, they are connected with a straight line and we get this. Okay. So location, point F is located, point S is located, and now we have connected F and S. Now let us move ahead. Next is we have to locate M1, and we are going to do that because M1 will be having coordinates of NM1, XM1. What is known to us is XM1 is known to us. That is sufficient. We can locate point M1 with the help of XM1. So XM1 will be located on y-axis. So here it is 0.21, and then after locating XM1, we will be moving on to the line FS, the line that connects points F and S, and wherever the intersection occurs, that point will be M1, and the x coordinate of that point is NM1. So if you want to know the weight fraction of solvent in the mixture, you can just read the value on x-axis. So it is around 0.325. So 0.325 would be the weight fraction of, so let me just note down. In this case, nm1, value of nm1 is 0.325. What is this? This is weight fraction of B in the mixture. Let us move on. Now, our job is to draw a tie line that passes through point M1, because the end points of this tie line, they are going to give us x1 and y1, and we are going to use x1 and y1 to find out the quantities of raffinate and extract phases. So let us draw the tie line, because the tie line will be drawn by trial and error. I'll tell you how to do that. So it is, let us first draw the tie. Okay, so let us continue. We have located point M1. Next is, as I said, we need to draw a tie line that is passing through M1, and we are going to do this by trial and error. And what is the trick? We will draw the tie line parallel to the closest given tie line. So the given tie line, this red tie lines are the tie lines that are given to us, the equilibrium data. So we will look at the closest tie line, and we will draw a tie line such that the tie line passing through M1 is parallel to the closest tie line. So for example, in this case, this particular tie line is closest to the point M1. So what we will do, we will draw a tie line that is parallel to this given tie line, and that passes through M1. I hope you are understanding. Our objective is to draw a tie line through M1. Now the given tie line is this one, which is closest to the point M1. So what I will do, I will draw a tie line that is parallel to this given tie line and which passes through this point M1. So we are doing this by trial and error. It has to be done by trial and error. So the black tie line that I have drawn would be the tie line that is passing through M1. What I have done, I have drawn it parallel to the closest given tie line. So the black tie line is the tie line that we need in our calculations. Now the next task is to locate the end points of this tie line, the tie line that is drawn through point M1. So this will give me y1, value of y1, the end point of this tie line, and the other end point will give me x1, and I need those values. These values are required for calculating E1 and Y1. So for this particular tie line, what are the values of x1 and y1? That is end points of this tie line, the black color tie line, which I have drawn through M1 and which is parallel to the closest given tie line. So for my tie line, the end points are x1 is 0.27 and y1 is 0.115. So that is what I require. I require these values to solve the material balance equations and get the value of E1 and Y1. E1 and R1, sorry. Okay, so let us use these values. So after we have found out x1 and y1, the next task is to find the quantities of extract phase and raffinate phase, E1 and R1 quantities. So the total material balance, we know it is M1 is equal to E1 plus R1. M1 is known to us, it is 140. So 140 is equal to E1 plus R1. I am calling that as equation 1. Then I'll be writing material balance for C. Material balance for C will be M1 into XM1, that is equal to E1 into Y1 plus R1 into X1. Now let us use the values. M1 is known to us, it is 140. XM1 is known to us, we had calculated it previously, it is 0.21. X1, we noted it as one of the end points of the tie line that passes through M1, So x1 is 0.27, y1 is 0.1115, the other end point of the tie line. And now just let us use these values. So it will be 140 into 0.21. M1 is 140, xm1 is 0.21. That is equal to E1 into y1 is 0.115 plus r1 into x1 is 0.26. So that is 29.4 is equal to 0.115 E1 plus 0.27 r1. And now I'm calling it as equation 2. So if you look at equation 1 and equation 2, these are two equations in two unknowns. Which are those two unknowns? E1 and r1. Let us get those unknowns. So from equation 1, I can write equation for r1 as r1 is equal to 140 minus E1. Now I'm going to use it in equation 2. So wherever there is r1, I'm going to replace that with this equation. So it will be 29.4 is equal to 0.115 E1 plus 0.27 into 140 minus E1. That is 29.4 is equal to 0.115 E1 plus 0.27 into 140 is 37.8 and 0.27 E1 minus 0.27 E1. So that is 29.4. This is brought on this side. So 29.4 minus 37.8. That is equal to 0.115 E1 minus 0.27 E1. That is minus 8.4 is equal to minus 0.155 E1. That is previously we got minus 8.4 is equal to minus 0.115 E1. That is 8.4 is equal to 0.155 E1. That is E1 is equal to 8.4 divided by 0.155. That is E1 comes out to be 54.19 kg. And since equation for R1 is 140 minus E1, so you can use the calculated value. So that will give me R1 is equal to 140 minus 54.19, and then R1 is equal to 80. That is, the subtraction comes out to be 85.81. So therefore, the quantities of raffinate and extract phases are thus obtained. R1 is 85.81 kg, the raffinate amount, and the amount of extract is 54.19. So in this way, we have to find out the quantities of raffinate and extract phases. The only important thing is drawing up the tie line that passes through M1. And for that, we are supposed to use trial and error method. And in my case, what I have done, I have drawn the tie line parallel to the closest given tie line. So any trial and error method we need to use in order to draw the tie line. And then after drawing the tie line, we have to note the values of x1 and y1, and then those x1 and y1 values are used to find out the extract and raffinate phases. So with this, I end my discussion. I end this short discussion where I have discussed one numerical for calculating raffinate and extract phases in single stage operation. In my next video, I'll be talking about multi-stage cross-current liquid extraction. So this was single stage liquid operation. In my coming video, I'll be talking about multi-stage cross-current liquid extraction. For now, thank you for being with me. Thanks for watching my video. Do subscribe to my channel. Tell your friends to subscribe to it. Hit the bell icon so that you'll be notified as soon as I upload any new video on my YouTube channel. In my next video, I'll be discussing multi-stage cross-current liquid extraction. For now, thank you. Have a nice day and hope to see you soon in my next video.